Okay. Why? That work better? Why am I hearing myself? Hey, buddy. That's weird. Okay. I didn't have this problem this morning. Why is it like this?
You're like you are muted, but there's another you in here that's not muted.
So I'm not. Oh, I know what's happening. I think the mic is picking. No, it's not. So the thing is, I'm using this one, the laptop, the one that just says Scott Conrad as audio, and I'm using my new webcam as the video, which is with my PC. Okay. Do I really need to admit everyone one at a time? Okay. Maybe I just need to turn it down. Oh, that's not too bad. I can live with that. I will be right back. Better? Okay. Can I just admit everyone in the waiting room? Why is it making me do this? Oh, let's disable waiting room. How about we do that? There we go. Okay. I'll be right back in just a second. So go ahead and figure out what problems you want to look at. And is it coming from here? Coming from here? Oh, it's coming from there. That's why. That's better. Okay. Never mind. We fixed it. All right. Okay, I'll be right back. All right. Sorry for the delay there. There we go. Okay. So, how is everyone doing?
All good.
That's good to hear. So what do we want to look at?
Quick question. Will the solutions for the practice exam be released anytime soon?
I don't know. It seems like everything keeps, okay, now I feel like, is my audio really far behind? Oh, maybe it's just, nope, I think I look okay. It looks fine for you guys? Pretty synced
It
up?
looks like it's matching up perfectly.
Oh, okay, cool. So I don't know, it seems like every exam, the practice problems come out later and later. So I'm not sure. I've done the ones, I've worked out, I think, 2468, something like that. I forget which ones I did exactly. 2, 3. I didn't do 3. Okay, well, I did some of the problems today in class. I could work out some others, and I'll post those. And I guess if we don't cover everything, then I'll finish up typing up the solutions, and I'll send those out via Canvas. But did everyone get the solutions that I did this morning sent out in the email?
Yes.
Okay, cool. Okay. Okay, so what do we want to look at?
Can we take a look at number 5?
Sure. Okay. So number 5 is we want to find and classify the critical points of following function. So f of xy is x squared y minus sine y on the domain so y lies between 0 and pi. Okay, so x is allowed to be anything, but y has to lie between 0 and pi. Okay, so critical points, we set both partials equal to 0. So partial with respect to x, what do we have?
Uh, 2xy.
We have 2xy. Set it equal to 0. And then the partial with respect to y, we have x squared, minus cos y equals 0. So from number 1, So the first equation tells us either x or y has to be 0. Or who knows, possibly both. We'll have to check the next equation. But at least one of those has to be true. X is 0 or y is 0. Second one tells us x squared is equal to cos y. Okay. So let's use this bit of info and apply it to the second equation. So suppose x is equal to 0. If x is equal to 0, then we have 0 equals cos of y. And since we know y has to lie between 0 and pi, what does y have to be? Right, it has to be pi over 2. That's the only value of y between 0 and pi for which cos of y equals 0. So we have the points 0, pi over 2. That's one critical point. And that is the only one corresponding to x equals 0. Now let's suppose y equals 0. So if y equals 0, which is allowed because, remember, you gotta be careful, have to make sure that's in our domain. It is because it's between 0 and pi. So if y is equal to 0, then x squared is equal to 1, which implies x is plus or minus 1. So we also have the points 1, 0, and negative 1, 0. So we got 3 points that are critical points. So we found the critical points. Now we got to classify them using the second derivative test. Okay, so f of xy we said was x squared y minus sine y. And we already said f sub x was 2xy, and f sub y was x squared minus cos y. Okay, so we know the discriminant is fxx fyy minus quantity fxy squared. So let's just write down fxx, fyy, and fxy. Okay, fxx is what? So fx is 2xy. So what's the partial of that with respect to x? It's 2y. And then similarly, fyy is sine y. And fxy is 2x. So our critical points, remember, so those were 0 pi over 2, and then 1, 0, and negative 1, 0. Okay, so let's plug these into our discriminant. So d of 0 pi over 2. So that is going to be pi. So y times 2 is 2 times pi over 2, which is pi, times 2 times x, which is 0, minus sine of pi over 2 squared. So sine of pi over 2 is 1, minus 1 squared. We get negative 1. Oh, I was like, this doesn't make any sense. My bad. Sorry, fyy is sine of y. Okay. Yeah, I was like, they're all going to be saddle points at this rate. Okay, sorry. fxx was 2y, which is pi. fyy is sine of pi over 2, which is 1. And then fxy is 2 times 0. So we get 0 squared. Okay, so we get 0 pi over 2. We got our discriminant is pi, which is positive. So if our discriminant's positive, we then need to check the sign of fxx. So our fxx is pi, 2 times pi over 2, which is also positive. So this point is local min, local max, or saddle point. Which one? The local min. The local min at 0 pi over 2. Okay. So let's check the at 1, 0 and negative 1, 0. Well, as we're going to see, we're going to get the same answer for both of them. So we get fxx, so 2 times y is 0, times fyy. Sine of 0 is also 0, minus, depending on which one we do, 1 squared or negative 1 squared. They're both 1. So for both of these, we get the discriminant is negative 1, which is less than 0. So then what does this tell us about 1, 0 and negative 1, 0? What do we get? We get saddle points. And so we've found and classified our critical points. So, any more questions about that one? It's a saddle point because the discriminant is negative. So there are 3 cases. If your discriminant is positive, then you have to check fxx. And then the sign works like the second derivative test for functions of one variable. If xxx is positive, you have a local min. If it's negative, you have a local max. If the discriminant's negative, then you automatically have a saddle point. And the discriminant for both of these guys is negative. Okay. So what else do we want to look at? Or anything you'd like me to discuss further? No. So there's not going to be any yeah, no, there's not going to be any questions on polar. That's interesting. I think the old book covered polar, but I think we're just going to cover that when we get to oh my god, I can't even remember what it's cylindrical coordinates. When we get to cylindrical coordinates, I think we'll take care of the polar. That is interesting. But yeah, definitely no polar in this one. Number 7, sure. Okay, so let's find the volume of the solid region under the parabolic cylinder z equals 1 plus y squared, and above the triangular region with vertices, in the xy plane. With vertices 0, 0, 1, 1, and 2, 0. Okay. So first thing we want to do is sketch our region. Well, let's write down what we're doing. So the volume under the volume of the solid under the graph of a function, which lies above a region D in the plane, we'll call this triangular region D. And here, so we're under the graph of 1 plus y squared. That's going to be our f of x, y. So the surface z equals 1 plus y squared is the graph of 1 plus y squared, the function of x and y. So our volume is going to be the integral over d of the function of which we have the graph, or the solid is under the graph. Okay, so we have our function. Really, all we need to do in order to evaluate this is find our bounds, and to do that, we need to draw D and figure out how we're going to do the bounds. So D, let's draw it in the xy plane. So it has vertices 0, 0, 1, 1, and 2, 0. So this is the region D in the xy plane that we're integrating over. Okay, so we're doing a double integral. We really only have two options so far for doing double integrals. We can treat it as integrate with respect to x first if it's horizontally simple, or y first if it's vertically simple. So is this region vertically simple, horizontally simple, both, or neither?
Horizontally simple?
Right, it's horizontally simple only. It's not vertically simple. So if we do the horizontal line test, we see that any horizontal line is always going to hit the left on this curve here, and the right on this curve here. And so we have a left curve and a right curve. However, if we do the vertical line test, we see for half of it, this is the top curve, and half of it, this is the top curve. And so if we wanted to integrate with respect to y first, we'd have to break it up into two integrals, which we'd rather not. So D is going to be horizontally simple. And since it's horizontally simple, the horizontal variable, y, is going to be the one bounded by functions. Oh, come on. That's our D. Okay. So we need the left and right curves. We need to write them as x equals some function of y for both of them. So I find it easiest, obviously, to write them as y equals something, and then getting x by itself. Sorry, this is 1, 2. Okay. So the left curve is just a straight line. It's y equals 1. Not quite. So the thing you multiply x by is going to be the slope, and the plus whatever, c, is going to be the y-intercept. So in this case, the y-intercept is 0. So it's going to be something times x plus 0. Right, it's y equals x in this case. right? The slope is 1. We go from 0, 0 to 1, 1. And of course, so if we want to get y by itself, x by itself, well, that's already done. So that's just the curve x equals 1. So for the right side, what's the equation of that one? It's going to be y equals what? Right, that's going to be negative x plus 2, or 2 minus x. So then getting x by itself, we get x equals 2 minus y. So then, let me give myself more room here. D is the set of xy. So x is going to be bounded by functions of y. X is bounded below to the left by x equals y, and above to the right by 2 minus y. And then y is going to be bounded by numbers. Y goes from what to what? Zero to 1. So then we can plug these into our bounds. Okay. So we integrate with respect to the function, the variable bounded by functions first. So we're going to do x first. So x goes from y to 2 minus y. We're integrating our function, 1 plus y squared. Integrating x first, and then y, which goes from 0 to 1. So let's do our inner integral. So integrating 1 plus y squared with respect to x, what do we get? What's the antiderivative? So we're treating y as a constant, integrating with respect to x. Well, 1 plus y squared is a constant, right? So then it just becomes that constant times x. So you go 1 plus y squared times x. And we're evaluating that from x equals y up to 2 minus y. So we get 1 plus y squared times 2 minus y minus y. And so we get 1 plus y squared times 2 minus 2y and let's multiply this out. To integrate it, when we do that, we get 2 minus 2y plus 2y squared minus 4y cubed. So that's our inner integral. We've integrated with respect to x. X is gone now. We're just left with y. And so we integrate that with respect to y. So we're integrating from y equals 0 to 1. the function 2 minus 2y plus 2y squared minus 4y cubed. And when we do that, we get 2y minus y squared plus 2/3 y cubed minus y to the 4 from 0 to 1. And so we get 2 minus 1 plus 2/3 minus 1, which we see as just 2/3. Let me make sure that's clear. Which is our answer. But like I said before, the important thing, making sure you can set up the integral. Evaluating the integral is usually not a ton of points because it's too difficult, but really important is getting the bounds correct on the integral. We good on this one? Okay. What else do we want to look at? It would. You're right. You're right. Sorry, Olivia. You're right. I thought that was 2y squared. Yep, it's minus 2y cubed. You're right. You're right. You're right. You're right. Thank you. Let me make sure I got more room here. So we get, sorry, 2y minus y squared plus 2/3 y cubed minus 1/2 y to the 4. Evaluated from 0 to 1. So we get 2 minus 1 plus 2/3 minus 1/2. So we get 1/2 plus 2/3. 7/6. Of course, this is a perfectly fine answer also. You really don't want to spend any time simplifying, and trust me, we won't judge. Yeah. Okay. What else?
You said that evaluating the integrals won't be a large part of the grade.
I mean, yeah, you need to be able to evaluate the integrals, but like if you do zero evaluation, I mean, you're going to get some points off. But if you make like an algebraic error somewhere, it's going to be you're not going to be punished very heavily for that. But usually, I think that the most points is going to be setting up your integral correctly. So if you got to this point here, you're going to be getting most of the points. Like if you can write out the integral correctly, you're going to be getting most of the points. That is assuming, so if you write out an integral that you could actually evaluate. So for the problems where you have to switch the order of integration, switching the order of integration, getting the bounds correct in the opposite order is obviously what you need to give me most of the points there. But yeah. If that makes sense. Make that more confusing than it had to be. Which is not to say you should not evaluate the integral, but if you're short on time, set up your integral, move on, and come back to it later. Number 10, sure. Okay, so D is going to be a region bounded in R2. It's going to be bounded by the parabola x equals 4 minus y squared. And the y-axis. So we want to find the absolute min and max of the function f of xy equals 2x plus y minus 1 squared on this region D. Okay, so we have a region in R2 bounded by two curves here. What we're doing is we're finding the absolute maximum of a function on a closed bounded set in R2. So as always, let's sketch this region. We're bounded by the y-axis, which is x equals 0. And we're bounded by x equals 4 minus y squared. So this is a parabola. So what is this parabola? How would you describe this parabola? So first of all, what direction is this parabola opening?
To the left?
Right. It's going to be opening to the left. And the x-intercept here is going to be 4. And the y-intercepts by setting x equal to 0 are going to be plus or minus 2. So it's going to look like this. And so this is our region D, the region bounded by these two guys, these two groups. Okay. So we have a closed bounded region. And so the way we find the max and min is we find the critical points on the interior, step 1, and step 2, we find the max and min on the boundary. So we kind of have two different ways to do step 2. We have the way we learned in 14.7. Let me do it this way. So number 1, we always need to find critical. So we're going to evaluate f at the critical points in D. We need to make sure if we find a critical point that it lies inside D, only considering the critical points which lie inside there. So we get some points, the critical points, we evaluate f there, as long as they lie in D. Otherwise, we ignore them. Step 2 is we're going to find the max and min of f on the boundary. So there are kind of two subcases. So if the entire boundary can be written with one equation, so suppose we have that equation, say g of xy equals k. We're going to use Lagrange to find the max and min on the boundary. So this is going to be like ellipses and circles mostly. We can write the entire boundary there as a single equation. However, if you get like a triangle, a square, or something like this, where you get two distinct curves and the region between them, you can't write the entire boundary with one formula, with one equation. So you're going to have to break them up into pieces. Otherwise, what you're going to do is you're going to evaluate f at the corners where the two pieces or two pieces meet. There could be more than two pieces, but where two pieces of the boundary meet. And then B, we're going to find the critical points of the transformed function f bar, like f bar 1, f bar 2, on each boundary piece. Right? So we're going to look at these one at a time. So we'll say L1 is going to be the left boundary and L2 will be the right boundary here. In this case, clearly, we can't write the entire boundary as one function. So what we're going to do is we're going to take our function f, rewrite it depending on what the points on the boundary look like. And then it's going to become a function of one variable. For that function of one variable, we find the critical points, we set the derivative equal to 0, and then we evaluate the transformed function at those points. Okay. So clearly we're in that case. because the boundary consists of multiple pieces. Okay, so step one. So we need to find the critical points of f which lie on side D. Okay, so f is 2x plus y minus 1 squared. What? There we go. Let me write that down so I don't have to keep going back. Two x plus or minus plus, okay. Okay. So let's find the critical points of f. So we set both partials equal to 0. What's the partial with respect to x? Right, it's 2. And the partial with respect to y is, of course, 2 times y minus 1. So, what are our critical points? For what points x, y are both f sub x and f sub y equal to 0? So there are none, right? Because the partial with respect to x is never 0. So there are no critical points. Cool. So that part's easy. 2. Now we go to the boundary. So we said left guy is L1, right guy is L2. So, well, let's do part A. We check the corners, and we check F. We find the corners, and we check F at them. So our corners are clearly what are the points where the two pieces meet? Well, it's going to be 0, 2, and 0, negative 2. And so we check F at those. So F of 0, 2, we got 0 plus 2 minus 1 squared, we get 1. And at 0, negative 2, we got 0 plus negative 2 minus 1 squared, we get 9. Throw that on our list that we're going to compare all our values to later. And then part B, we need to, for each piece of the boundary, transform our function and find the critical points of the transform function. So on L1, so what are the points on L1 look like? So well, L1 is the equation is the line x equals 0, right? So x is always equal to 0. Y can be whatever, but y has to go from -2 to 2. Right, does everyone see that is what all the points on L1 look like? X is equal to 0, y is whatever. So we plug those into our function f. We put x equals 0, y equals y, and we'll call that f bar 1 of y. So we just get 0 plus y minus 1 squared, which is just y minus 1 squared. So now it's a function of one variable. This is our transformed function. And we're going to find the critical points of this from y goes from -2 to 2. So we take the derivative and we set it equal to 0. Well, the derivative is just 2 times y minus 1. We set it equal to 0. And so the critical point comes at y equals what? Right, y equals 1. And so we check the transform function at y equals 1. So f bar 1 of 1 is equal to 1 minus 1 squared, which is 0. Add it to our list. So we write what our points look like based on the equation of the curve that corresponds to the piece. So the left curve is x equals 0. So x is going to be 0, y is going to be whatever, y. And y goes from -2 to 2. It's now a function of one variable. We find the critical value of that function, the critical points, by taking the derivative, and then plug in those critical points into the transform function and check it out. So for L2, we do the same thing. L2 is, well, L2 is the equation x equals 4 minus y squared. So then y is going to be whatever. And x is going to be 4 minus y squared. Those are the points on our L2 piece of the boundary. And once again, y is going to go from -2 up to 2. Does everyone see where I got the equation for these points on L2? Right, so that's the line, or the curve x equals 4 minus y squared. So then the points on there, the x coordinate is going to be equal to 4 minus y squared, and then y is just going to be y. So then plugging this into our equation, oops, 4 minus y squared, not x squared. So we get 2x, so 2 times 4 minus y squared. Plus y minus 1 squared. So I'll just simplify this. We get 8 minus 2y squared plus y squared, so negative y squared. So minus 2y plus 8 minus 1 plus 7. No, sorry, plus 8 plus 1, so plus 9. So this is our second transform function. Okay, so let's find the critical points of the transform function. Well, let's take the derivative. F bar prime of 2 is going to be negative 2y minus 2. Set it equal to 0. Once again, we get y equals 1. Nope, we get y equals negative 1 this time. Sorry. And so then plugging that into our transform function, we get negative 1 squared minus 2 times negative 1 plus 9. So we get negative 1 plus 2 plus 9. So we get 10. So our step 3 is we put all our values together that we got from steps 1 and 2. So we got nothing from step 1. From step 2, we got 1, 9, 0, and 10. The largest is max, the smallest is min. So our max is going to be 10. And our min is going to be 0. As long as we did not screw anything up. That's right. Okay. So any other questions about this one, or do we want to look at another problem? So why can't you use Lagrange? You could. You could. You kind of could, but you would have to use Lagrange separately for each piece. And you'd also run into a problem using Lagrange. So with Lagrange, you have to have a constraint equation, right? And the constraint equation tells you the points you're considering. So the points you're considering, the constraint equation is going to be the equation of the boundary. So if the boundary consists of two pieces, each of which has a different equation, you're going to have to use Lagrange for one and then Lagrange for the other. It's going to be two separate problems, which you could do, but it's probably going to end up being more work. Moreover, we run into a small problem here. So if we use Lagrange here, say for L1, if we say x equals 0 is the equation there, so our g of xy is just going to be x. And the set of points for L1 is just x equals 0. But we're only considering the points x, y, where y lies between -2 and 2. So we could get some points where y lies outside of that, and we'd have to throw them out, which is doable. But it's something you have to be careful. I would just, I think this is probably the easiest way to do it when, I'd say each of these is easier than doing Lagrange for each boundary piece. If you can write it all in one piece, then definitely do Lagrange. That's going to be the easiest way to do it. But if it's multiple pieces, you would have to do Lagrange multiple times if you wanted to, but that's why. So it looks like we just have 9, 3, and 1, which I haven't done yet. So, I mean, if no one has any questions, I can go over 1. Cool. I'll just do 1, 3, and 9 if no one has any other questions. So let's do number 1. So problem 1. So we need to find and classify good Lord, guys. The critical points of the function f of xy is x cubed plus 2y squared minus 6xy plus 5. So finding the critical points, setting both partials equal to 0. So the partial with respect to x is going to be 3x squared minus 6y, set it equal to 0. And the partial with respect to y is going to be 4y minus 6x. And we're going to set that equal to 0. So from the first equation, we get the y, when we get y by itself. So 3x squared is going to be equal to 6y. So dividing both sides by 6, adding sides, we get y is going to be equal to 1/2 x squared. And so we're going to plug this relationship into the second equation. When we do that, we get 4 times 1/2 x squared, which is 2x squared, minus 6x equals 0. And so we can factor out 2x. We get 2x times x minus 3 equals 0. And so from this, we get x is either equal to 0 or x is equal to 3. So using the info from here, we can get y if x is equal to 0, then y is equal to 1/2 times 0 squared. So y has to be equal to 0. And if x is equal to 3, y is equal to 1/2 times 3 squared, which is 9/2. So we get the point 0, 0, and 3, 9/2. Those are our critical points. So now we need to do the second derivative test to classify them. Okay, so fxx is going to be 6x f sub yy is going to be 4. And f sub xy is going to be -6. So the discriminant at 0, 0 is going to be fxx at 0, 0, which is 0, times fyy, which is 4, minus f sub xy, which is -6 squared. So we get 0 minus 36. So we get -36, which is negative. And so what can we say about 0, 0? Local max, local min, saddle point. Saddle point. Right, Oh my God. Come on. And then we check for 3 9 over 2. So we get fxx is 6 times 3, which is 18, times fyy, which is 4, minus fxy squared, which is negative 6 squared. So we get 72 minus 36, which is 36, which is positive. So our discriminant's positive. So then we check fxx. So fxx at our point 39 halves is 18, which is positive. So we have a local min. At the point 39 halves. Ooh. So if no one has any objections, I'm going to go ahead and do number 3. Sound good? All right. So number 3, we need to evaluate the following integral. So y goes from 0 to 1, x goes from root y to 1. We're integrating x cubed plus 1 square root of that, dx dy. Okay. Chances are we're not just going to give you a straightforward integral with bounds and all. That all you got to do is evaluate. Chances are, if we give you the bounds, you're probably going to have to change the order of integration. Probably, unless you're feeling exceedingly generous. So let's see if that's the case here. If we were to do this integral. So first we integrate square root x cubed plus 1 with respect to x. Can we do that using what we know from 140 and 140? Can we evaluate that in our integral? We cannot. So as given, we cannot evaluate the inner integral. So that's telling us we're going to need to change the order of integration. So we need to switch the order of integration. Okay. So step 1, always with switching the order of integration, is we need to sketch our region. Okay. So x is, so it's going to be bounded on the left by x equals square root of y. And on the right by x equals 1. So let's draw those guys. So this is a curve x equals 1. X equals square root of y is going to be the top half of y equals, sorry, the right half of y equals x squared. So x equals square root of y is, so right, if you square both sides, you get y equals x squared. But since x is equal to square root of y, square root of something is always positive. So we're only getting the piece of that of y equals x squared where x is positive. So we're getting the right half of that guy. So that's our left bound. X equals 1 is our right bound. And then y goes from y equals 0 up to y equals 1. Well, notice these guys hit when y is equal to 1. And so our region that we're integrating over is this guy here. We'll call that D. Okay, so well, currently we've been treating this as a region that has a left curve and a right curve and integrating with respect to x first. That didn't work for us. So now we're going to need to change the order of integration. We're going to need to integrate with respect to y first. So we're going to look at this as a region that has a top curve and a bottom curve. So first of all, is it vertically simple? Can we write this all in a single integral? If we intersect a vertical line, any vertical line, are we always going to hit the same top curve and the same bottom curve? I'll answer it for you. Yes, D is vertically simple. So we want y to be the guy we integrate with respect to first. So y needs to be bounded by function. Okay. So what is our bottom curve? Y is equal to what? All right, so this is our bottom curve, the x-axis. And so that's y equals 0, right? And then our top curve is x equals root y or y equals x squared. So y is going to lie between 0 and x squared. And so then x is going to go from 0 to 1. And so then changing the order of integration, we got y goes from 0 to x squared, x goes from 0 to 1, integrating x cubed plus 1 square root. And so really quickly, doing the integral, integrating with respect to y, x cubed plus 1 is just a constant, so we get y times square root x cubed plus 1. Evaluating, from y equals 0 up to y equals x squared. And we just get x squared square root x cubed plus 1. Plugging that in to our inner integral, we get the integral, x goes from 0 to 1, of x squared square root x cubed plus 1. Lo and behold, now we can use sub. And when we use sub, we see we get, so 1/3 times 1 over 2/3, so 3/2. X cubed plus 1 to the 3/2. Evaluated, x equals 0 to 1. And we get, so that's 1/2, 1 to the 3/2, or 2 to the 3/2. Oops, hang on. Sorry, let me. Don't forget this 1/2. So 2 to the 3/2 minus 1. And that's our answer. 1/2 times that. Wait. Sorry, it should be 2/3. So it should be 2 over 9 times. Yes. Classic change the order of integration problem. And why not? I'll go ahead and do number 9. Seriously. Knock it off. So we need to find and classify critical points of f of xy equals 2x cubed plus 5x squared plus xy squared plus y squared plus 7. So set the partials equal to 0. Partial with respect to x is going to be 6x squared plus 10x plus y squared plus, that's it. Set it equal to 0. Partial with respect to y is going to be 2xy plus 2y. Equals 0. Okay, so this one's a little more complicated than the others. So we don't really get much of a direct relationship between the two variables. from either of these. So what we're going to do is we're going to look at the second function, the second formula. And we'll get a definite value for x and y. Definite possible value. We'll get different cases. So for 2xy plus 2y, we can factor out the 2y. When we do that, we get 2y times x plus 1 equals 0. So from this, we get either y is 0 or x is negative. Those are the only two possibilities which make f sub y equal to 0. So for each of these, we're going to apply these to the other formula and figure out what the other variable has to be. So when we apply y equals 0 to the equation, we get 6x squared to the first one. 6x squared plus 10x plus 0 equals 0. Which we can factor out 2x. We get 2x, 3x plus 5 equals 0. So then x is either equal to 0 or x is equal to negative 3/5. Sorry, negative 5/5. And both of those are correspond to the case y equals 0. So from these, we get the points x equals 0, y equals 0, and x equals negative 5/3, y equals 0. Now let's do the same thing for x equals negative 1. We plug that into the first formula. We get 6 times negative 1 quantity squared. So we get 6 plus 10 times negative 1. So 6 minus 10 plus y squared equals 0. So we get y squared is equal to 4. So y is equal to plus or minus 2. So we got x equals negative 1, y equals 2, and x equals negative 1, y equals negative 2. For our 4 critical points. Okay. So let's, we found the critical points. Let's classify the critical points using the second derivative test. F sub xx is going to be 12x plus 10. F sub yy is going to be 2x plus 2. And f sub xy is going to be 2y. Okay, so 0, 0. Our discriminant is going to be fxx, which is 10, times fyy, which is 2, minus fxy squared. Fxy is 0. So we get 20, which is positive. Since the discriminant's positive, we're going to check fxx. We get that that is 10, which is also positive. So we get a local min. At 0, 0. And then for negative 5/3, 0. Fxx is going to be negative 20 plus 10, so negative 10. Fyy is going to be negative 10 over 3 plus 6 over 3 is going to be negative 4/3. Minus fxy, which is 0, squared. So we get 40 over 3, which is positive. Discriminant's positive, so we're going to check fxx. When we do that, we get negative 10. Fxx is negative. So then we get a local max at negative 5/3, 0. And so we need to check negative 1, 2, and negative 1, negative 2. So negative 1, 2. Fxx is going to be negative 2. Fyy is going to also be negative 2. Nope, it's going to be 0. Sorry. And fxy is going to be 4. So we get negative 16. The point's negative, which means we get saddle points. At negative 1, 2. And then doing the same thing for negative 1, negative 2, we see we get the same thing. So fxx is going to be negative 2, fyy is going to be 0, fxy is going to be negative 4 squared, but that ends up being the same thing. And so we also got a saddle point at negative 1, negative 2. And so that's one of the more complicated problems to find the critical points of. But it usually doesn't get too much more difficult than that. Any other questions? Nope. Okay. Well, if you don't have any other questions, I'll hang around here until 7:30. If you decide at some point you have something else you'd like to ask. And if not, I will see you guys tomorrow, and good luck on your exams. Have a good one, guys. What are you doing, dude?
Oh,
Yes.
told me you played Sekiro. Did you know that they released like a comic for like that one guy in it?
Oh, the Hanbei or
Yeah,
whatever.
Han Baby Undying.
Yeah, I think that's the only one I know of. I haven't read it.
Like I saw it and like it was like here's a free preview and I was like, oh, all right, I'll check it out. I was like, all right, cool.
Yeah, I thought that was interesting. I guess he's the character. I mean, he's an incredibly minor character.
Yeah, no, I thought it's you literally just all you do is stab him. And
Right. Yeah.
it was like what's the point of him having this? But it's like whatever, man. It's cool.
I mean, it's interesting. It's like, how did he get this centipede thing inside of him? I guess that's kind of interesting. But yeah, I don't know. I'm not much of a manga guy, but yeah, they have that. Yeah, apparently Sekiro is getting an update in like 8 days too, which I'm kind of excited about.
What's it bringing?
So they're getting a boss rush, which is whatever because we already have a boss rush mod, but they're getting something. It's like a gauntlet of strength, which is just basically it's just like, I guess, progressively harder challenges. We don't know that much info about it, but it's just going to be like progressively harder challenges or something, and you keep going until you die, I guess. But you can unlock skins in game with that too, which is whatever because we have like 20 trillion skin mods on PC. But
Thank
it'll
God
be
I
interesting
can
if they do.
unlock
If
all
they
these
do.
cool skins.
There are only going to be 3 skins though available. Which is
If it's free, it's free.
Yeah.
Oh, have you ever played Blasphemous?
I have not. I've seen some people play Blasphemous, and it looks pretty interesting.
Yeah.
It's kind of a Souls-like sort of game, right?
Yeah, I would say it's in that sense. I like this. I actually, I've beat it. I'm planning on playing through it a second time because they've added like a free DLC, but you have to beat the game first and then do a new game plus to actually access it.
Oh, that's kind of lame.
Yeah,
An
but like
interesting DLC.
at this point, like everybody who like got the game is most likely I guess beat it. So like for me, it's just like all right, just gonna start right over. They also added like challenges to it, I guess. Like they like you start the new game plus and then it's like all right, so you can do this so that like there's one because in the game you can cast like spells like Dark Souls, so it makes it so that the spells deal more damage but that you like don't deal like any like physical damage, I would say.
Oh, interesting.
And for
Yeah,
me
I
that would be
haven't
a
I
thing
haven't
to
gotten
do.
around to playing Blasphemous, but it looks pretty interesting.
Yeah.
But I've seen a few people mess around with that.
All right, well I Well, I just have work to do.
All right.
All right. See you.
Have a good one, man. See ya.